Hello everyone, this is Bill Dees with David H. Paul Incorporated. Welcome to our webinar today. We're going to be talking about advanced troubleshooting using membrane element autopsy. And let me get this going right. And first off, I'd like to introduce David H. Paul Incorporated. For those of you that may not have attended to any of our training, we're a world leader in high-tech water treatment training. Since 1998, primarily in membrane technology. We also have high purity, including ion exchange and EDI and others. Our training includes online training like we're covering today. We also have seminars with classroom hands-on that we present at our facility, and we can also do on-site training at yours. Have training will travel. Our technical service division also, we will do or can do reverse osmosis membrane element autopsies. Of course, that's what we're here for today, to go over what we cover on our membrane element autopsies. We also have other other technical services as the screen shows here. Today's webinar, we're going to be doing a 40 to 45 minute presentation with a 15 to 20 minute question and answer at the end of it. You'll see in another slide here in a minute, anytime you have a question, go ahead and type that into the questions box, and we will answer those at the question and answer period. This presentation is being recorded. We will have a link up on our website here in the next day or so. Once we get it posted, here's a link that we'll have this at with that recording. We'll also send you out a thank you email with a PDF of this presentation, and then also a reminder of what the link is for this recorded webinar. As I say, the question and answer at the end of the presentations, go ahead, but anytime you can go ahead and type in your questions in that questions box, and then we'll answer as many as we can at the end of the session, very last section there. If we do not cover all the questions that are asked during the webinar, we will be answering those offline, but those also will be included on the recorded webinar, of course, that we'll post later as soon as we get that up. Give my background, as I say, my name is Bill Dees. I work for David H. Paul Incorporated. I've been in water treatment, though, since 1988. I've been with David H. Paul specialized in membrane technology since 1999. Also, I am in the consulting aspect of it, and then also one of their instructors for David H. Paul. I'm also reverse osmosis specialist 4 certified through David H. Paul Incorporated. So getting into our webinar today, our purpose here is, of course, starting off with an overview how to perform an element autopsy, and then also how we can use membrane element autopsy as an advanced troubleshooting tool. Why we want to perform an autopsy to begin with here, most of the time there can be, or a lot of times I should say, there can be multiple problems and can be difficult to troubleshoot the RO system. And once you start having issues with this, trying everything you can think of, some of these troubleshootings, all your other troubleshooting has failed, you may have to go to an element autopsy. Element autopsy is the last thing you're going to be really looking at. Or if you have to have a relatively fast fix, you might want to have an autopsy done. Keep in mind, membrane element autopsy is going to be a destructive test. We are going to cut apart this element and dissect it, find out what actually happened to it, so you won't be getting this element back. Now, we can have multiple problems in some of these element autopsies, which can be difficult to find without doing that element autopsy. So you're going to have to be really on top of your game to be able to catch it without doing that autopsy. So these are some of the ones that we have seen, multiple problems here that could cause this issue that you would need to have that element autopsy done. Also, some of the things you might be doing before you have an element autopsy, of course, looking at the data. looking at your log books, trying to figure out what's going on. That doesn't tell you what's happening, of course. You may have to have that element autopsy. This includes also the performance trends, your chemical cleaning performance, design review, all of this, the feed water analysis. If you still cannot figure it out, then that's, like I say, most commonly when you have an element autopsy done. So starting off this first section here, we want to make sure everybody's on the same page. So I do have a little bit of a basic information on membrane elements so that you can know that what we're talking about on these membrane elements, what's inside of them. So of course there's several manufacturers of membrane elements. These are basically, they look and work the same. They're basically interchangeable from one manufacturer to the other. But the only thing you have to change inside the pressure vessels is the elements themselves, but also the end cap adapters and interconnectors. There's three basic building blocks to these spiral wound elements. We have our membrane, we have a feed water spacer, and a permeate spacer. So here's a drawing of what I'm talking about with the membrane, and here's a picture of what I'm talking about of an element that's been unrolled during an element autopsy of the membrane itself. Next, we have a feed spacer, and just as we have drawn here, here's a close-up picture of the crosshatch material. This allows water to enter into our wraps of membrane so that the water can come in contact with our membrane itself, and of course the pressure force the water through into the permeate. We need to get that permeate out of the membrane element, so we have a permeate spacer, and just like the drawing shows here, there's channels woven into that permeate spacer that allows the water to go down towards our permeate tube, which we'll see here shortly, and then that permeate tube will allow that water to exit out the element and the RO system. So the three building blocks, again, like I say, we have our membrane, feed spacer on one side, we have the permeate spacer on the other, and then to make a full envelope or leaf, what's known as a membrane envelope or leaf, we have another membrane on the other side, and then it's glued, sealed up all the way around that to make an envelope so that we can keep that feed water from coming in contact with the permeate there. Now that feed water enters into our wraps of our feed water spacer, and it of course crosses through and exits out as the concentrate also. So this is also known as a cross flow filtration. One flow in, two flows out with the concentrate and the permeate. As I mentioned previously, we need to have some way to get that water out of the membrane element. So we have a permeate tube that has holes in it. And so here's our drawing of it. And here's a small home drinking water element on a rolling machine. And as you can see right here, that's the permeate tube that has holes in it. And then our permeate water carriers down here below. They're going to attach that permeate water carrier to the permeate tube. And that's what they're doing here. They're gluing it to it. And then they're going to wrap our membrane on these little home drinking water elements. We're going to wrap the membrane around it and then glue it on the very end there, and then also down the side, and then seal it around the permeate tube on either side of our envelope. And that's what they're doing in this picture right here. You can see down here on the bottom left-hand side there where they have the pneumatic glue gun. Now there can be auto glue lines to glue these envelopes together. The auto glue lines are going to be a more uniform glue line, a thinner glue line or a narrower glue line also, so you get more square foot of membrane in the element. Or you can have hand glue lines, and yes, still today there are some manufacturers that hand glue the lines of their membrane elements. And as you can see, the glue lines right here are not as uniform as what you'd like to see, especially like right here. That's where the two glue lines, one guy over here gluing it and another guy, a similar, over here gluing it, and that's why they have more larger splotch of glue right here. And then it's not as even over on this side. So as I say, you can have hand glue lines still. We're going to have one envelope or leaf with that feed water spacer in there. It allows the water to enter. And here's a picture again of the feed spacer. That water comes in and goes through, exits out the concentrate. Due to the pressure from either the high pressure pump or the city. The water passes through the membrane, gets into the permeate water carrier, goes through those channels down to our permeate tube, and then exits out whichever end is easiest for the plumbing or the piping coming out of the RO system. When we make, or when they make the larger diameter elements, it doesn't make sense to use one envelope or leaf, so they're going to use multiple envelopes or leaves. So we have a 4x40 all the way up to one manufacturer had an 18-inch diameter by 16-inch long element. It just would not make sense to try and use one envelope to make these larger diameter elements, so they put multiple envelopes in there. And when we do multiple envelopes, what we're talking about, of course, permeate water carrier directly attached to the permeate tube, and then some of the permeate water carriers indirectly attached, as we're showing right here. And then we have our membrane, folded sheets of membrane placed in between that with feed water spacer in between there. We then have the very ends of them glued together, and then these two right here will be glued together. These two right here will be glued together, and then this one will wrap around and glue together with this one, and of course encasing or enveloping our permeate water carrier on the other side there. And here's an example of multiple envelope membrane element. Next section we're looking at is potential problems. This, of course, can be from scaling. Potential problems can also be fouling, chemical attack, manufacturing defects, permeate back pressures, and then there's possibly others. That's the main ones that we see. First off with scaling. Scaling is our mostly double charged ions coming together above saturation and laying out on the membrane. On our left-hand side, we had so much scale on this one that it even laid out on our fiberglass outer wrap. The one on the right-hand side, of course, we have calcium sulphate laid out on the membrane. So this is, of course, our definition of scaling with the precipitation of dissolved feed water substances due to concentration within an RO unit above that 100% saturation limit. Now, since it is concentrated ions that cause scaling, our issue with scaling is going to be at the back end, our highest concentration of our ions. In this case here, that last two elements that have yellowed out, those generally are the ones that will start scaling up first. Our next potential problem is fouling. This can be from our sand, our silt, our clays, bacteria, other contaminants that can bond together, lay out on the membrane. Here we see biological fouling both on the membrane itself and also on the feed spacer. And of course, here is our definition of what we're talking about with fouling. Now, since we're talking about suspended solids coming into the RO system itself, of course, with our feed water, that's where our suspended solids, bacteria, whatnot, is going to be coming in with. Plus, the very first element in each pressure vessel on that first stage is going to have our highest water flux rate into the permeate. So that's where our fouling will generally start occurring, is that very first element in each pressure vessel, first stage. Chemical attack. Chemical attack is, of course, where we're starting to get damage on our membrane itself. Most commonly, this is going to be from chlorine coming in and then burning holes in the membrane, but it can be any oxidizing agent that can cause us, of course, membrane damage or chemical attack with membrane damage there. Now, where that occurs, there's a couple ways this can occur. If we have rust particles coming in, those rust particles are going to get trapped by the feed spacer in that very first element, and it's going to act as a catalyst to the chlorine, and it'll burn holes in that very first membrane. If we do not have rust particles, then due to the recovery rate, 75% recovery most common, and the concentration factor of the RO system, the highest concentration of anything in that RO is going to be the very last element. So as I say, a 75% recovery RO has a concentration factor of 4 times. So in theory, whatever trace amount of chlorines we had come in on our feed on this RO system, of course, we're going to have concentrated up close to 4 times at the back end. So that's where our first damage is going to occur, is at the very back end of the unit. Next, we have manufacturing defects, and as the name implies, these are the membrane element manufacturer making mistakes, essentially. In this case here, we see a crease right along right here, and that basically what happened was when they glued it together, the glue started setting up before they could roll it up. That glue usually slides on itself a little bit as they roll it, and in this case here, it already set somewhat, and so it could not slide upon itself. So now what happens there is it creases, it folds the membrane right along that crease, and you have a sharp edge there which can have holes in the membrane now. Other manufacturing defects can be, of course, the chemistry aspect of the casting of the membranes themselves, as we see here. That's very, very uncommon to see. As far as I'm aware, that's the only time we saw this problem, was this particular element right here. We also can have what's called osmotic blistering. And osmotic blistering is the blisters you see right along here on the glue line. The glue did not adhere to itself like it should have, and what happened is the water will then penetrate the membrane, but since there is glue around that blister now, it can't exit the element, and you have all these little blisters there. And you're not going to be able to see this unless you have an element autopsy performed. Of course, you may have higher pressure drops because of that, but that blister, like I say, you're not going to get that water out of there. The other thing the osmotic blistering does is it weakens the glue line, so now you can have ruptured glue lines because of the osmotic blistering. And then permeate back pressure. This is, of course, from getting too high of a pressure on the permeate side compared to what you have on the feed side. All it will take is approximately 15 psi or 1 bar of pressure or less, sometimes higher than what your feed pressure is. So in other words, 0 pressure on your feed side and 15 psi or 1 bar of pressure on your permeate side, and it creates these blisters that you can see right here from that permeate back pressure. This one was so bad that it also ruptured the glue line, so we had a lab spatula stuck through where that glue line had ruptured right through here. So that's what you're seeing here, is a lab spatula stuck in there. Permeate back pressure can occur whenever you have a valve on the permeate line. Eventually, or sometime, it may get shut off, and then you turn off your high pressure pump, and of course it ruptures or causes that causes that permeate back pressure to occur. Or it could also occur during cleaning CIP, clean in place, and you deadhead the permeate, and that permeate has nowhere else to go. You're not making much water during the chemical cleaning, but it does build up pressure with a little bit of water that does pass through there. So where the permeate back pressure occurs, whatever's closest to the header, permeate header, coming out of the RO system. If it's on the left-hand side like we're showing here, of course those first elements on the left-hand side will have the permeate back pressure damage. If it's on the right-hand side, we'll see the elements on the right-hand side being damaged. Now, since we're going to be taking apart, cutting open these elements, we also have to, of course, talk about autopsy safety. Since we're cutting the fiberglass off, you run the risk of getting cuts, especially with your hands and whatnot. So we recommend wearing a heavy-duty glove, leather glove, so that you don't have cuts occurring. Eyes, of course, since you have this fiberglass, most commonly, you're having to cut it open. Getting in there, you should wear safety glasses and prefer goggles and maybe even a face shield. Since we're using power tools, a lot of noise coming off this, we recommend wearing earplugs while you're cutting the fiberglass off. And then since we're having to pry most of the fiberglass off after we cut it off, again, you could get pinches, so again, wear gloves, the heavy-duty gloves, leather gloves. Since we're cutting the fiberglass, we will have some fiberglass floating around. in the air, so we recommend wearing a dust mask or face mask so you don't breathe in that fiberglass. The other issues you can have with element autopsy is, since most of the time every element we have, almost every element we have, is some bacterial growth in there. So we don't want to, of course, be handling that, and then of course getting sick from the possibly getting sick from the bacterial or biological growth. So again, wearing gloves. This time we're talking about nitrile gloves or latex gloves, and then also wash hands, possibly even wipe in with alcohol, or wash your hands with alcohol. And then the final thing is, of course, with chemicals that could be going in through the RO system during normal operation, and or when you're doing the actual autopsy itself, we recommend wearing gloves and goggles. So now getting into the actual autopsy itself, our autopsy reports, of course, we're going to have the breakdown as we're seeing here on the page, with our introduction, information, shipping and receiving, and so forth. We'll get into the external construction, internal construction, foulant evaluation, membrane performance, microscope evaluation, and then, of course, additional analysis and statement of results. So I'm going to go to actually this is 2 or 3 different autopsies that we've done in the last couple years, all put together to come up with a example or sample report that we are going to be going through on this webinar here. So to begin with, of course, we have our title page, and that is going to be a final report for who we're going to be giving the autopsy for. So that's where in client, of course, we're going to have the name of the company that's doing it. The next section down here, we're going to have what membrane manufacturer it is, and then also what model, serial number, where it came from, and then the date of the actual autopsy when we finished up the report. Our next section we have is the table of contents. That goes without saying, so I'll jump over that. We then have our executive summary. Very first thing, this is what we found in there. So right away you will find out what's the main concerns with this element. In this case here, inlet and outlet organic fouling of the feed spacers, as we'll see as we go through this. And then there was other issues with it that we have listed. This next section, we do a little bit of schooling of whoever's having the element autopsy done. So we have a breakdown of what an element, how it's made, what's the membrane elements consists of. So that just shows you, similar to what we just went over in this webinar. Same thing with design of the RO system, and then we also define what we mean by stages, and then also first pass, second pass. This next section, autopsy tracking, of course, is going to be the contact person and their phone number, email, and so forth. When we have someone contact us to have an element autopsy performed, first thing we do is we send out a questionnaire for them to fill out. This questionnaire is going to have information that we use during the autopsy that will help us figure out what's going on with it. And of course, the very first thing we ask them in this questionnaire is where the raw water source was from, where it's coming from. We then also have if it was ever chlorinated or not. We ask what the temperature is of the feed water coming in. We'll then want to find out a little bit about the pretreatment in front of the RO system, and then what the startup date of the system is. We'll then have them define what the makeup of the RO system is. In other words, what the array is to begin with here. In this case, it was a large RO system with a 48 pressure vessel the first stage, 24 in our second, and then the third stage had 12 elements in it, or excuse me, 12 pressure vessels in it. We have a pressure drop. If they know what the pressure drop is across each stage, we have them list that out. Number of elements per pressure vessel in each stage, and then also the RO unit permeate and concentrate flows are important. We want to find out if they will mix membranes around in the RO system. So for example, this unit, which is unique, they had different model membranes in each stage. It was somewhat of a hybrid RO system, trying to balance out flux rates and experimenting also somewhat with this particular design, and that's why they have different model membranes in each one of those stages. We have also the location of the membrane element listed here. That's where we got that for the very first page on that title page, where the element came from. And then if it has ever been moved around in the RO system, we want to know that, or if it's always been in the same location from that number 11 question above. We want to find out how often the unit is shut down and for how long, and then also what the water is used for is also listed in our questionnaire. If there's any information, or if they do clean in place, we want to have that information, also how they do the cleaning. That'll also help us during the element autopsy. Next section we go into, first thing we want to do is look at the shipping container and see if there's any damage during the shipping. And we'll note that in our report just to make sure that anything we find in the element maybe it was caused by the shipping. We want to make a note of that just so we can refer back to that. So that's that section there. We don't have any pictures of that, but we do take pictures during the unboxing of it just so we have that information that we can always go back to it if we need to. The next section we talk about the membrane element, and we get into look at the manufacturer of it and also what the model number and serial number is of that particular element. We then weigh it. Before we do anything else, we want to weigh, see how much it weighs. A new element, most commonly, these 8 by 40, 8-inch diameter, 40-inch long elements weigh around 31 to 33 pounds. There are some that are way more than that, but the most common weight is going to be, like I say, 31 to 33. And as you can see, this one does not have a whole lot of in there, foulant or whatever in there at 31.1 pounds. But we might make a note of that. We'll then do a vacuum hold test. We'll put a 25 to 30 inches of mercury vacuum on our permeate tube and then isolate it and then see if there's a decay of that vacuum. We'll let it sit for 2 minutes, and essentially if you have a 6-inch change in mercury per minute, that'll indicate a presence of a leak on that element. And of course, that'll tell us that we have an issue that we need to take a look at. We'll then look at the external evaluation and look at our fiberglass, see if there's any cracks in that fiberglass, any issues with it, any wrinkles, any indication of bypass around the outside of the elements, whatever we can find. In this case here, this one looked pretty good. There's no issues with it. Also, you'll notice we have the direction of flow on there, and of course the brine seal is up here on the feed end here also. Next thing we do is we look at our brine seal plus also the feed and concentrate anti-telescoping devices, or ATDs. And all three cases, the brine seal, the ATD on the feed, and the concentrate in this particular case, they had no issues. Sometimes we may see bent spokes. Now, Hydronautics makes a very robust anti-telescoping device, as you can see, so there's no issues on this one, but sometimes we'll see a bent spoke. We'll see impact indications on the outside edge of either the feed or the concentrate sometimes, indicating that that element has been dropped. In this case, we do not see that on any of the, either end of this. So overall on this one was a pretty good shape. We will get the odor from it, our best discernible odor from this, come up with the best description we can come up with. In this case here, it just had a wet smell to it. But sometimes these elements can be rather rank when we open them up. So we want to, of course, note that so that we can have that on our element autopsy also. We will then cut open, or actually, excuse me, we will score the end around the anti-telescoping device and knock those off or pull those off. or in some cases we'll have to even cut through the spokes with a modified bolt cutter to be able to get in there and get that anti-telescoping device off there, because we want to see the rafts of membrane, the scroll, while this is still intact before we start opening it up. And in this case here, you can see on the feed end here that on the close-up picture there's a yellowish tannish foulant on almost every wrap of membrane there. There's also on the further back, a wide shot, there are some spots of a dark foulant on there, and we take pictures of that in this case here. And as you can see, that looks like an organic or maybe biological foulant up close on that membrane, or those scrolls, I should say. We do the same thing on the concentrate end. Now this is that same element, and as you can see, there's quite a bit of a foulant coming out at the back end of that element. Pretty heavy foulant coming out there. We will then cut the fiberglass off and then pry it off, and we'll unroll the element. We'll get into more of the unrolling here, show you a wide shot of it here in a little bit. But as we're unrolling this, without disturbing the feed space or the foulant that could be in there, we will take pictures, and also we will have a video that we will link to. We'll put up a YouTube video and link to that with our autopsy. Then you can come in and click on this picture. Now this link is not valid on this one. I've taken it out on here. But we would click on this and it'd go to a link on YouTube showing the video of the first few inches of the feed, and sometimes on the concentrate end we'll do the same thing, showing how much the foulant is on the very front end of that element, or on the concentrate end there, the very back end of it. In this case here, we only had maybe an 1/8 inch to 3/16 of an inch of the foulant getting trapped on the very front end of it. If we ran this video, which will not work on the webinar, that's why I took the link off. If we ran this video, you'd see the camera scrolling up across that feed spacer, and you'd see very little foulant actually laid on the membrane itself and or on the feed spacer. But that's why we do this. We want to see how much foulant is on there. So we include videos in our reports. In this case here, since we found some kind of unusual things on this element, we found foulant on the very front end and on the concentrate end, and usually the foulant is heavier on the feed end of a first element like this. Well, the concentrate end, we had more foulant coming on this one. The only thing we could surmise, and plus it's dry, somewhat dried compared to the moisture on the feed end of this. So what we surmised on this one, when they stood it up to drain it out for shipping, some of that foulant maybe have ran out the back end or the concentrate end of this element, and it built up on the concentrate. So that's why you see a heavier foulant on that concentrate end. So normally we wouldn't have pictures like this, additional pictures like this, but in this case it was something unusual, so that's why we do have it on there. And of course we also have the direction of flow noted on those pictures. We'll then count how many number of envelopes or leaves and spacers the element has in it. In this case here, it had 25 envelopes and leaves, or envelopes and spacers, feed water spacers in there. We'll then also take a wide shot of our membrane, and in this case here, it also had the feed spacer laying on there, just looking to see how much foulant on there. And as you can see, the blue tint is the actual feed spacer on these hydronautic membranes. But as you can see, there's very little foulant actually laid out on that membrane. We'll then also do membrane close-up. And as you can see, there was a little bit of foulant further into the element on the feed end, but overall, laid out on that membrane, there was not a whole lot. Most of it was on the very front end of it and the very back end of it with that foulant. We will then do a carbonate test, and what we do there is see if carbonate scaling will drip hydrochloric acid on there, and if there's any effervescing or fizzing occurring, of course there's carbonate scale, and the effervescing, and or fizzing is going to be the carbon dioxide being liberated out of the scale. In this case here, there was no carbonate scale, but the membrane surface was bleached somewhat with the hydrochloric acid. That's why it turned this white color right here. So that's where that hydrochloric acid was dripped and bleached out the membrane, or the foulant that was laid out on that membrane. We then inspect closer the feed water spacer. We'll measure it with a caliper, see how thick it is. And then also we will, as for contrast, we'll put a piece of copy paper in behind there with the serial number on there, showing the contrast of the copy paper and the foulant laid out on that, caught on that feed spacer, so you can see how much foulant is going to be on there. In this case here, you can tell, you can very easily see that copy paper through the feed spacer. So there's not much foulant on it. We'll then cut open the membrane, looking at the back side of it to see if there's any irregularities or abnormalities of the backing material of the membrane itself. And then also we look at the permeate water spacer and see if there's any abnormalities of that. This one had a very small issue, wasn't a big issue, we didn't even make a note of it. They had a little bit of a line of a glue right here. That's what we're seeing here, is a very thin 1/8 of an inch or less glue line, like they dribbled glue on there. Not a big problem, but that's what we're seeing right there. And then we also have a close-up of our permeate spacer shown here. We'll then inspect our permeate tube and glue lines. Permeate tubes, every now and we'll have one that has been crushed so much that they'll break the permeate tube, but generally speaking, we don't find too much issues with the permeate tube. We'll look at the width of their glue lines, and also we will see if the glue goes all the way to the edge, but also what the glue line strength is like, and we'll also have a video of that. Again, a link to YouTube with the strength of that glue line, pulling it apart. So again, we would set this up and start the video and try and pull apart the glue line so you can see how strong the glue lines are. Sometimes from high temperature or chemical attack, the glue will soften up and it'll just zipper apart. It'll pull apart very easily. Most of the time though, the glue lines are very strong, very difficult to get apart, and sometimes it actually will tear up the membrane getting it apart. We'll do a membrane performance. We'll do a cell test, take sections of the membrane, put them in a cell tester, and we will run standard test conditions that the manufacturer will define. In this case here, 150 psi, applied pressure, 1,500 milligrams per liter sodium chloride, 25 degrees Celsius. And they had a 19.5 gallons per square foot a day. So every square foot of membrane, on average, in this membrane element would have 19.5 gallons pass through it in a 24-hour period. And it had a salt rejection of 99.7%. Well, Hydronautics in this particular membrane said it should have a 25 gallons per square foot a day of flux rate, so we're below that, and it had a 99.6% salt rejection, and so the salt rejection was very good on this one. And we also graphed this out, as we can see right here. Same time with our cell test, we'll do a dye test. We'll put some coupons of the membrane in a cell tester and run a large molecular weight dye through. That dye is a purple color, and there's always going to be organics and or bacterial or biological growth on the feed side that absorbs that dye, so it always turns purple on the feed side. So that's normal, but if we saw any dye on our permeate side over here on the right-hand side, that'd mean we'd have damage to the membrane. In this case here, there's no damage to it. There's no dye penetration to there. So this one passed the dye test. We will do a foulant evaluation where we'll take a weight boat, weigh it, see how much it weighs when it's dry and clean. We'll then scrape one membrane and put all of the foulant off of one membrane envelope inside that weight boat, and that's what we're seeing right here. So as you can see, this particular envelope had very little foulant on there. We'll then dry it, evaporate the water away from it, and we will then weigh that weight boat afterwards and determine how much foulant per element is inside there. In this case here, very little foulant was inside this particular element. We'll do a microscopic evaluation. This is actually the feed side of another membrane. This is not the same membrane that we've been looking at. As I said, we have 2 or 3 of these put together. But this one is interesting in that it is a filamentous type foulant laid out on that membrane. So here's a close-up picture of it. And then we also have videos of the same thing, as you can see down below here, with the microscopic pictures and videos. We'll do a loss on ignition. That's part of that membrane the foulant identification or foulant evaluation we had previously with that weight boat. In this case here, we'll take that weight boat and put it in a muffle furnace at 550 degrees Celsius and burn off any organics. So we'll have what's called loss on ignition. In this case here is 94.9% loss on ignition. And we have also a graph on this. So that almost 95% organic foulant that was on this membrane, that's one of the highest we've ever seen, David H. Pohl Incorporated has ever seen laid out on a membrane like this. Usually it's not as much of a breakdown or a more even breakdown of these. We will then have EDS and FTIR analyticals evaluation of the membrane foulant. And the first section of this has a breakdown of what we found on this membrane, in this case here protein, bacteria, and then a cellulosic component, for example, plant matter or algae or something like that. They also found a little bit of inorganics on there, and they have those listed out. The rest of this is boilerplate of how they do the SEM, scanning electron microscope pictures, along with the EDS and FTIR analysis. So I'm not going to go over that section, but we do have also the, of course, SEM pictures that we're showing here of the foulant itself laid on the membrane. We'll also have the electron dispersive spectroscopy, EDS, breakdown, and we have percent by weight of the different elements that they found on this. Now, since the membranes are made out of carbon and oxygen, that's why most of this is up there, very high concentrations here. So they also will do another table doing the same thing, but removing the carbon and oxygen out of there, so they can have a breakdown of just the other elements in there. And then they have the EDS spectra of the foulants, the Fourier transform infrared. Every compound will have its own infrared signature, and that's what we're listing out here, or showing right here. And then the FTIR image is what we or what they had the lab took pictures of and did the FTIR on. 2 different sections here, and then they have the spectra, the reference spectra, what they're comparing it to find out what was laid out on that membrane. So in this case here, this is the membrane itself. This is bacteria with a protein, and then the cellulosic breakdown, and carbohydrate polymer was what they found on the membrane. Now this one was a little bit different, so they also did another, or we also had another one done of the back end foulant. Same thing, more FTIR, EDS analysis done on that. That's the same thing that we just covered on our previous section. So I'm just going to skip over this. It's the same idea though, looking for what they had on the, or what we had on the membrane. And then here's the reference spectra. They found a polyester molding compound along with thermoplastic polyester. And what it was, this was a tertiary effluent that was a feed water to this one of these RO membrane element autopsies we did in this report, sample report. And then here's a breakdown of the, again, of the reference spectra with the protein, bacteria, and cellulosic. We then have a statement of result, what we found, a breakdown of the findings in the report, and then we have a discussion of what we found with inlet plugging, outlet plugging, and so forth in this particular one, and then we have recommendations on how to fix this. We actually have 2 different levels of RO autopsy, element autopsies, and the top of the line, of course, we have recommendations along with consulting, 30-minute telephone consultation that we can do. And then this is boilerplate with a release of liability with our report. So that is our report. As you can see, it goes on for that one in particular went on for something like 50 pages. So we have a quite in-depth report that we do with these element autopsies, but that is our report. Which elements to autopsy? If the problem is the first stage, we want to, of course, autopsy the lead element. If the problem is the last stage, we want to do the tail element, the very last element in the RO system. So this is showing the first stage. Pick one of those elements in any one of those pressure vessels and send it in. If it's a second stage problem, we want to grab that last one, very back end of the unit, and have that autopsied. So how you find out, find our information on our element autopsy. Here's our website, davidhpaultraining.com, www.dhptraining.com. You go over here on our technical services, click on that. That'll bring us to this page, and then you have the autopsy services. You click on that, and that'll bring up our website, and then it'll have a breakdown of the autopsy services we have, and then a contact form on our website. As I say, we have two levels of autopsies. One, report of findings. That just lists out what we find in there, and we don't go into the troubleshooting and consulting of the element autopsy on that aspect of it. And we charge $24.99 for that, and we have a 2 to 3 week turnaround from when we get that element to when we get that report to you is usually 2 to 3 week turnaround. We also have our other level of autopsy, with report of findings with recommendations in there on how to fix it, and then up to a 30-minute telephone consultation. We charge $29.99 for this, and again with a 2 to 3 week turnaround on this. So what I'm going to do now is I'm going to open this up to question and answers. So if you guys have any questions, go ahead and type them in to the question box, and then I'll be answering those as we go along. So Daryl, what's our first question? So what we have first is how much amount of ozone can destroy membrane in parts per million. It's a very aggressive, ozone is a very aggressive oxidizer, so it's going to take very small amounts of ozone. 1 part per million, maybe even a little bit less, even a half a part per million, will do damage over time. I'll give you an example on chlorine. 1 part per million, manufacturers will say 1,000 part per million hours. If you have 1 part per million, it would have a doubling of salt passage after 1,000 hours of operation. Well, ozone is, like I say, a very strong oxidizer, so it's going to be very similar to the chlorine. I don't have an exact parts per million number for you to give, but just be aware we don't want to have any oxidizer going in there. Next question. Next question is, do you recommend for using from different membrane in each stage? We can do this. We usually call these a hybrid RO system, and what we're trying to do is balance out the flux rate by using different model elements, usually from the same manufacturer. I really don't recommend changing manufacturer to manufacturer from one stage to the other, but you can do, like I say, different models trying to balance out the flux rate, water flux rate of the RO system. It's a good way to balance it out so you have a more consistent flux rate to the RO. And basically what the goal is to actually get more water passing through the second stage than the first stage, so it cuts down or reduces the amount of fouling potential of that first stage. You basically have to do a analysis using the membrane manufacturer's design programs to try and see what's going to work the best for you with these hybrid type systems like that. If you're interested in something like that, we'd love to help you. We also will help with the technical services aspect of that. Give us a call. Next question, can we eliminate particulate and biological fouling by UF pretreatment? Particulate matter, yes. Ultrafiltration, UF, you're going to be a 0.01 to 0.05 micron particle, or excuse me, pore size. And so any particle greater than that will be filtered out by this ultrafiltration. The bad news, there's one contaminant that will pass right through an ultrafilter. It's a dissolved contaminant that will cause this issue in the RO system with particulate, and that is basically it's the organics. Dissolved organics will pass through an ultrafilter and feed the bacteria that are in the piping and the RO elements and RO system itself when they built it. So an ultrafilter is not an end-all be-all to stop fouling of an RO system. Yes, it'll get the feedwater particles filtered out as long as there's no damage to the ultrafilter, but it will not stop the biological fouling of an RO necessarily. Next question is, what do you use to scrape foulant from an envelope? Plastic spatula, and the answer to that is yes. We have a couple different spatulas. Some are a wide one, a good about 4 inches to 6 inches wide, and then we have a little small one, a little nylon one that is a couple inches wide that we scrape it off of. Depending on how much foulant we have on there, will determine which one we use. Next question. Can the membrane surface analysis pick up degradation caused by chlorination and differentiate from the sulphite copper oxidation? First question there, the surface analysis pick up degradation caused by chlorination. Generally what we're looking for on that is, of course, the vacuum hold test and then the dye test. If we have those two fail, we will also do what's called a Fujiwara test. Fujiwara is a test looking for halogens that could come in contact with the membrane. There can be a lot of false positives with Fujiwara, so we don't usually do it, but sometimes we'll do the Fujiwara. The actual analysis, surface analysis, generally will not show it. So my answer is going to be no. I've never seen that we can pick that up on there. The sulphite or the copper oxidation, it will show those laying out on the membrane itself, and it'll give us a clue, but it will not give us a particular, yes, this is what caused it. It'll just show that they're on there. Next question. Do you ever see fouling caused by the antiscalant? Antiscalant by itself it's a negative charge, long chain molecule, man-made molecule, and the membrane, RO membranes are a negative charge. So if we slightly overfeed the antiscalant, no problem. It'll just be rejected by the membrane, go down the drain. We have run into, I should say, last couple of years though, where the scale inhibitor pump has malfunctioned, and while the unit was shut down, or I should say the check valves in there, and it started siphoning scale inhibitor from the day tank directly into the RO system. And since it was just direct scale inhibitor getting in there, and scale inhibitor can be a real sticky polymer in there, it laid out and did plug up the membrane just because it was a straight scale inhibitor getting in there. That's very uncommon to see. The other thing you can see though, we have run into this here last couple of years a couple times, is that you can have a cationic polymer injected in front of a clarifier or a media filter, something like that. That cationic polymer, as the name implies, is positive charge. The antiscalant is going to be a negative charge. Not all cationic polymers, not all antiscalant will interact, but we have seen, like I said a couple times, where they attract to each other and form this snotty mess and then lay out on the membrane itself. So it's a cationic polymer scale inhibitor interaction that is actually plugging up the membrane in that case. But the antiscalant itself, we rarely see that actually plugging up membranes. Next question. Do any manufacturers have spacers that inhibit bacterial growth, and do they work? Well, that pictures that we saw in my report, That is from hydronautics. They have their LD membranes, and that LD is that blue feedwater spacer. It has an antibiological, antibacterial compound permanently molded into that, kind of like some of the Chlorine countertops. You can get that antibacterial compound molded into those. It's the same thing with the blue feedwater spacer that we saw in those pictures, and they do work to some extent, but we still have found some of the membranes, not picking on hydronautics by any means. It just sometimes there's so much biological coming into that RO system that feedwater spacer cannot actually take care of it. Next, we have installing a valve on permeate line could cause back pressure. But when I shut down an RO unit, the membrane should be kept wet. Can you explain? Well, I understand what you're getting at there, but the issue being is if that valve is shut off, you got to be careful, and that eventually is going to be left on when you turn on the RO system, or left shut off, I should say. And when you turn on the RO system, you will start getting higher pressure buildup on the permeate side. And of course, you get 70, 80, 100 pounds of pressure on the permeate side. First thing you're going to do is shut off the RO system, and now you damage the membrane. So we don't recommend putting the valve on the permeate side. We would have, and this is one of the reasons why they'll do this, is let's say you have a storage tank that RO permeate's going into. Generally speaking, they'll have a pipe coming up to the very top of your storage tank, and that'll keep water going back into that, on that permeate side. Now, keep in mind also, though, there is also going to be check valves on your permeate side, keeping back pressure from going back, or from keeping the osmosis from completely draining your permeate side. But that being said, we don't recommend putting ball valves, shut-off valves on the permeate side, because eventually you are going to have a issue with that permeate back pressure. Next question. We are interested in trying chlorine dioxide in our CIP. Some manufacturers seem to say it's okay, while others don't recommend it. What is your experience? Well, I'll go with that very last question there. What is our experience? David H. Paul Incorporated has no experience with chlorine dioxide coming in contact with RO membranes. But what we have seen, what we have read about, is chlorine dioxide can be used in RO membranes. I've heard as high as 200 parts per million of chlorine dioxide can come in contact with it. I would recommend getting in touch with the manufacturers of the chlorine dioxide units, or you can even buy now liquid chlorine dioxide and have it shipped in, although it can degrade rather quickly. So check on that, and what we find, you should be able to do it. Do your homework first, though. We're getting close to the end here. I might have time for one or two questions left here. Our next question then is, do you recommend UV lights in front of an RO unit? And what we're talking about on a UV light for controlling biological growth is a 254 nanometer UV light. And what happens with UV light, it inactivates. It basically doesn't kill the bacteria. It changes, it alters their DNA where they cannot reproduce. But it won't get them all. You cannot have a 100% effective UV inactivation. So what you'll have, let's say you have even a 99% inactivation, and you have 100, this is just easier for you to understand. If you have 100 bacteria per milliliter entering into this RO system, 99% inactivation, that means you're going to have one bacteria that's active, able to reproduce, going into that RO system, and 99 that are not going to be able to reproduce. What will happen is that one that's able to reproduce, they will start growing in there. The 99 that cannot reproduce, they'll end up dying off and decomposing. Now they become food for the bacteria that are still viable, able to reproduce. So our experience with UV lights in front of an RO system is they won't necessarily control the bacterial growth in that UV. There is a time and place for UV lights. We just don't agree with trying to control bacteria in that RO system itself. So we have never had any luck with it. So if there's any other answers, we've come to the end of our webinar today, so we will be answering the rest of these via email. And of course, we'll be sending out a link with our webinar of this. So keep in mind, we have our technical service with our with our membrane element autopsy. We'll also do chemical cleaning evaluations, telephone consulting, on-site consulting, and others. So here's our information for contact. And the last thing I asked you to do as you're exiting, we have a evaluation as you're exiting. It's just a one-question evaluation. Please evaluate this webinar today. And again, I thank you guys for listening, and have a great day. Thank you.